kind of fun to apply the transformations to sine and cosine waves to applications. And here we have the St. Louis, Missouri average low temperatures, and 48 is the line of equilibrium. That gives us the average low, or the middle of the road average low temperature for St. Louis. The amplitude is 23. That tells us how high we go above and below that during the year. So in July, the average low temperature is 71 degrees, 23 degrees higher than 48. And in January, the average low is 25. That is 23 degrees lower than 48. Notice that the frequency is 2 pi over 365. So there's this relationship between frequency per 2 pi and the wavelength. The frequency is equal to 2 pi divided by the wavelength, and vice versa. If you do algebra to solve that for W, then the wavelength is 2 pi divided by the frequency. So you could rewrite this as W equals 2 pi divided by the frequency. My pen's not working very well on this paper. There we go. So anyway, if I take 2 pi and I divide by the frequency, I get the wavelength. So notice it's 365. Well, how many days are in a year? 365. So it makes sense that my wavelength, my average low temperatures, span a pattern that lasts a year. Now, the 200 is the horizontal shift, and remember that we are talking about cosine. Cosine normally starts at a maximum at 0. So if we've shifted that maximum to 200, it means we're shifting it to the 200th day of the year. Well, when is the 200th day of the year? It is July the 19th. So I'm hitting my maximum average low temperature in the middle of July. Now we have another example. These are the tides at North Head Bay in New Brunswick, Canada. I know that looks like CA for California, but it's Canada. And this was on a specific date. Again, due to the cycles of the moon, the waves are not the same every day of the year. So this was April 8th of 2020. And our formula is 11 times sine of pi over 6 times the quantity x minus 9.66 plus 12. So the 12 is the line of equilibrium. That's the average height of the water at North Head Bay, New Brunswick on that date. And the amplitude is 11. So the high tides are 11 feet above 12 feet. So 11 plus 12 is 23. So 23 is where we're hitting these maximums. And then 12 minus 11 is 1, so these minimums are at 1 foot. Then the frequency is pi over 6, and if you take 2 pi, which is, how many radians are in a full circle, and you divide by the frequency, you get the wavelength. And in this case, if we clean that up, the pi's divide out and I get 12. So, what does that mean? Well, my X unit, my input, is hours. So every 12 hours, we are repeating the high tides, and that's true. If you live near the ocean, you know that. You know that, every half day, you're getting high tides and low tides. So again, there's practical meaning to the line of equilibrium, the amplitude, the frequency, and the wavelength. The 9.66 is your horizontal shift, and here we're working with sine. So if I shifted to the right 9.66, I want to look for a point on the line of equilibrium where there's an upward hill. So that's how many hours into the day. So 9 o'clock going on 10 o'clock, so somewhere between 9 and 10 o'clock is when I'm hitting the average height of the water. And then I hit it again on the way, when the tide's going out. And then 12 hours later, I'm hitting that point again. So that's what the 9.66 is. It's, you know, because this was written in terms of sine, it's telling us where we're hitting the line of equilibrium.